So let's talk about another wave property that sound exhibits. Um, let's start though by looking at a way to visualize sound. So here's it's an animation that lets us visualize sound. All right, so this is an effectively a point source, right? So we have a single speaker, and what we're looking at is compressions and rarefactions of the air, right? So if there is no sound, how do I turn this off? If there's no sound, the medium is gray, right? This is atmospheric pressure, and when there is sound, there are rarefactions, which are black, and compressions, which are white. Or maybe vice versa, it doesn't really matter. I will point out here that we can change the frequency, so if we lower the frequency, we can see that the wavelength gets longer. If we increase the frequency, the wavelength gets shorter. That's because the wave speed is staying where it is. You can actually hear this. At least you're supposed to be able to. Never mind. It will show you particles, though, which is also interesting. We've seen illustrations like this before. And you can see it all at once. Look at that, it's fabulous. Okay, but what happens if two sources of sound sit in the at different locations, and the sound is allowed to sit on top of itself? Meaning, the sound from one speaker and the sound from another speaker live in the same space, right? They travel through the same medium and they interact with each other. What does that look like? Well, it's different. It's different than what happens for, say, particles, right? If I throw a baseball and then I throw another baseball and they occupy the same space at the same time, they will bounce off of each other. Waves, however, are not baseballs. Waves are energy, and the energy will actually pass straight through. Alright, so if I turn the second source on, what you see is interference. What you see is interference, and what I want to show you is this, that in the regions that are gray, the molecules don't move around very much. Alright? Those correspond to places like, I don't think I can annotate this. So along those regions that are gray, the particles don't move around very much, whereas along the regions that are black and white, the particles move around a lot, right? I think you can see quite a bit of that. So this is a phenomenon called interference, right? In the regions where the particles move around a lot, this is constructive interference. In the regions where the particles don't move around much at all, that's destructive interference. Let me show you another illustration. So this is a wave on a string. This also shows constructive and destructive interference when pulses touch each other. So I'm going to send a pulse down this string, and you can see when it bounces off of the ends, it has a couple different kinds of behavior, right? It can either flip or it cannot flip, depending on whether the end is loose or fixed. That's useful for another idea. We don't need it right now, but I wanted to show you this. So let's slow this down and send another pulse. So those pulses pass through each other. And these pulses are also going to pass through each other. Right? So they're not bouncing off of each other, they're just passing through. But an interesting thing happens when they sit on top of each other. Right? So these two pulses are both negative. We'll step it forward. Right? And when they sit right on top of each other, they add together to make one big pulse. Right? There's kind of our one big pulse. That's constructive interference. All right, and here these two pulses are about to pass through each other. Now one is positive and one is negative, so when they sit on top of each other, they cancel each other. So here, look at that. That looks like there's nothing going on, right? Because the displacement of everything, the pulses are sitting right on top of each other and they exactly cancel. At least their displacements cancel. But if we keep going, the pulses pass through each other. They haven't canceled each other in the sense that they no longer exist. They simply interfere destructively. All right. So when this happens for, say, sound, constructive interference is loud, destructive interference is silent. All right. Light actually does this as well. Constructive light interference is bright, and destructive light interference is dark. Okay, so let's describe this mathematically. So let's say I have a speaker. Perfect. And this speaker is emitting some sound. And let's say I have a second source that is identical. So I'm going to copy this if I can. I'm going to try. Perfect. Okay, so if this is what happens, right, this is constructive interference. But if I move one of these, by, say, half of a wavelength, now this would be destructive interference, because you see, no, not what I wanted. You see that the peak here sits on a valley there, and a peak here sits on a valley there. It's going to cancel always, right? So what if I wanted constructive interference? Well, I could move this, nope. I could move the second wave further still. All right, if I move that second wave a complete wavelength, then the waves sit on top of each other again, and peaks align, and valleys align. This is constructive interference again. So again, how do I ensure constructive interference? Well, what I need is the path length difference. The path length difference. So what does that mean? Well, let me move that arrow, actually. No, that's fine. So let's put a listener right here. So if someone was listening here, they would hear constructive. He would say, I hear a loud sound. Because it's constructive interference, right? So the requirement for that, if we look at path lengths, so I could say this could be path 2, this could be path 1, and the path length difference better, is in this case path 1 minus path 2. But we see what really matters is this distance right here. That's my path length difference. Sometimes we call that delta D, right? That is a wavelength. So if the path length difference equals a wavelength, it's constructive interference. In fact, if the path length difference equals an integer number of wavelengths, right? It could be 2, it could be 3, it could be 4. We have constructive interference. So if the path length difference is in lambda, it's constructive. If the path length difference is a half lambda or lambda plus a half or 2 lambda plus a half if the path length difference is an extra half. So we could say n plus a half lambda. That's destructive. So what matters is the path length difference. So let's do a simple example and then a not as simple example. Let's do example number Let me go back here to find it. 9. Two loudspeakers are 42 meters apart and facing each other emit identical 115 hertz sinusoidal sound waves in a room where the speed of sound is 345 meters per second. Okay, so let's talk about that for a second. If speakers interfere constructively and destructively at different places in a room, how does a stereo work? Right? Wouldn't there be quiet spots in the room and loud spots in the room? And the answer is, well, it depends on frequency, right? Because it's, for constructive, remember, constructive, delta D, which is my path length difference, equals in lambda. And for destructive, path length difference is in plus a half lambda. But lambda is related to frequency, right? So if you have, like, actual music playing, that's lots and lots of frequencies. So yes, for some frequencies, in fact it'll be for a set of frequencies, the location that you're standing will indeed, if there are two sources, like two speakers, there are some frequencies that are destructively interfering at that point. But there's so many other frequencies going into the sound that you don't notice. So what you need for to actually measure this sort of thing is a single frequency. Imagine like the pitch that you might use to tune an instrument or something. Like here. That's a pure frequency. That's 440 hertz, right? Which is an A, I think. So that's not very interesting. You don't usually just listen to that for fun. Okay, so let's do this example. We've got two loudspeakers that are facing each other, emitting a single frequency. We could actually emit that. What is it? 115 hertz? 115 sounds like this. Oh, it's very low pitched. Yep. Not hearing it. It's too low. Try one more time to make it louder. Nope, my speaker won't do it. That's fine. So the laptop speakers are very small. They don't do it very well. So there's one speaker and the other speaker is sitting over here. And they're each emitting this 115 hertz sinusoidal sound, and they're emitting presumably in phase, meaning when this speaker is emitting a peak, this speaker is also emitting a peak in the same wavelength, even though I can't draw very well. So we just copy it. I wonder if I can just duplicate there. It's perfect. Look at that. It's perfect. Okay, so the question is, Susan is walking along a line that connects these. Right, so nope, what I actually want is this. There. So they're in a line. Susan's walking along this line. As she walks, she finds herself moving through loud and quiet spots, right? Because the path length difference will be an integer number of lambdas, and then an integer plus a half, and then an integer, and then an integer plus a half, as she walks along this line. So at one point, she's standing 18.75 meters from one speaker. So she is, the full distance is what, 42 meters? And at some point, she's standing like here, which is 18.75 meters. So this is continuing to emit. So the question is, what does she hear? Is it loud? Is it quiet? Is it somewhere in between? It doesn't have to be constructive or destructive. It's just more interesting when it's one of those for us mathematically. Okay, so what do we need to do to figure this out? How do we know if it's constructive or destructive? Well, we're going to test. We're going to say, does it fall into one of these? Right? Because I can figure out delta D, and I can figure out lambda. And if I take the ratio of those, that's going to be a number. And if it's an integer, this is constructive. If it's an integer plus a half, right, like 1.5, 2.5, 3.5, then it's destructive. If it's something else, if it's like 3.76, this is not constructive or destructive. I might be able to say it's closer to one than the other, but like 3.75 is actually exactly in between a whole and a half. So that's our procedure here, is to figure out the path length difference and lambda, and then take the ratio to see if we're in one of these two. Okay. So the path length difference, well, if this path is 18.75, then this path is 42 minus 18.75, which is 23.25. And then delta D is the difference of those. And we're going to use the positive, all right? It doesn't make sense to have a negative number here, because in is never negative and lambda is never negative. So delta D is implied to be positive. So delta D is the bigger number, 23.25 meters minus 18.75 meters. And what I get for that is, where are you? 4.5 meters. Yeah. Okay. So what's the wavelength? And this is confusing. It's like, oh, 4.5 meters. Well, then it must be destructive. No, we just found delta D. We need to divide that by the wavelength to see how many wavelengths fit into that. So what is the wavelength? Well, I'm given a frequency, and I know that lambda times f is v. So if I divide by f, I'll have lambda, right? And I know v that was given to me. I think it's 345. Stop moving. 345 meters per second divided by 115 hertz, which is a per second. And what I get when I do that is 3 meters. And again, it's easy to look at that and say, oh, 3.0, that's an integer. So then it must be constructive. No. What we need is the ratio of delta D and lambda, right? Delta D divided by lambda is 4.5 divided by 3, which is 1.5. That is what's sitting in front of lambda. So when I say, I could solve this and say delta D then equals 1.5 times lambda. Is that constructive or destructive? Well, going back up to these, that's destructive, right? That's n plus a half. So n equals 1, and it's 1 plus a half. That's destructive. So this is going to be a quiet spot. Okay, I think that's good for now. There's a whole other type of problem you can work, which is, let me just find some blank space so I can draw a picture. You could say, what if I have a speaker, draw it facing the other way. What if I have a speaker here and a speaker here, and I stand like here? Do I hear a loud or a quiet sound here, or something in between? So now I need like D1 and D2, but it's the same procedure, D1 minus D2, and I need a wavelength. You could also ask this. You could say, I'm standing at this location. For what frequencies is the sound loud? For what frequencies is the sound quiet? In that case, you're actually solving for an infinite number of things, right? You would say delta D equals N times lambda. Or if I'm looking for a frequency, you could write that as N times V over F. Then you could solve for F, but it would be a function of N. So then you plug in all the possible N's, which is 1, 2, 3, 4, and so forth. So that would let you solve for all of the frequencies that are constructive or destructive if you use N plus a half here.